So in the late 1700s, the study of matter was revolutionized by the quantitative analysis of reactions, which had been greatly improved by more accurate. And I found this video that I've included here just to show what we are working on now. It's something called a chemoscope. Again, a better piece of equipment that will give us a greater insight into the making and breaking of bonds. They equate it to better microscopes. So in the late 1700s, the study of matter was revolutionized by the quantitative analysis of reactions, which had been greatly improved by more accurate balances. More accurate balances. We've talked about this already quite a bit, that the better the equipment, the better the data. And I found this video that I've included here just to show what we are working on now. It's something called a chemoscope. Again, a better piece of equipment that will give us a greater insight into the making and breaking of bonds. Okay, I could not get that video to work, so that's a technical issue I'm going to have to work on, but we need to move on, so I'll just show you that in class at some point. So we have several laws that developed from the fact that we had better equipment. And the first one is the law of conservation of mass or matter, and it states that mass is neither created nor destroyed during ordinary chemical reactions or physical changes. So the mass of the reactants, what you're putting together or mixed before the reaction happens, like our baking soda and our vinegar, equals the mass of the products even though they are different molecules after than what we started with. Okay, and we talked about this, or we will talk about this when you try to do your lab to prove or to support this law in the baking soda and vinegar. And you will learn that this law of conservation applies in something called a closed system. Okay, if we have an open system, it allows gases and things like that to escape, so the mass will end up being impacted unless you can get it in a closed system environment. And I have written here, this will be the basis for balancing equations. That's why we balance equations, because of this law. And if you'll look right here, I've got a little image here. We've got a sulfur atom with a weight 5.325, and then we've got an oxygen molecule 5.314 times 10 to the negative 26, and you'll notice that they react, they yield, this sign means yield, SO2. And if you'll look at the mass of the SO2, it's the sum of the masses of both of the reactants. So that is what balancing equations is. You notice you've got 2 oxygen molecules here, 2 here, 1 sulfur here, 1 here, and that is the basis of the law of conservation of mass. Our next law is the law of definite proportions, and it is also known as the law of constant composition. And it states that the elemental composition of a pure compound is always the same proportions by mass. So the pure compound is always the same proportion by mass. And note, this means that compounds made in the lab should not be fundamentally different than compounds found in nature. I know we have a lot of disagreement about that, and we tend to think things in nature are better versus those in the lab. But this law says that if they are the same chemicals, they should have everything the same proportion by mass, and they should fundamentally be the same. Our example is sodium chloride, table salt. It always consists of 34% by mass of the element sodium and 60.66% by mass the element chlorine. So simplified, we could say salt is always made of one sodium atom and one chloride atom. Take a look at our figure here, especially this part, the math part. We will be working, at least in some of my classes, on determining the percent mass or the ratio, going back to find the actual formula when you're given the mass or the percent mass. And so you'll notice that when you do the math, by the way, they got the grams for these from the periodic table, and I'll teach you about that. So they got the mass of each oxygen and nitrogen, and then they just did the division to get 16 divided by 14 was 1.14, 14 divided by 14 was 1. And then because things have to be in whole number ratios, they just rounded those down to 1 nitrogen and 1 oxygen. And here you'll notice when you do the math, you've got 32 divided by 14, so you get 2.28. So you end up with 2 oxygens to every 1 nitrogen. Our last law of interest is the law of multiple proportions. Notice 2 and 3 sound a lot alike. It states that if two elements, A and B, combine to form more than one compound, then the masses, the masses of B that can combine with a given mass of A are in the ratio of small whole numbers. And I touched on this above when we were talking about the percent by mass, in the ratio of small whole numbers. So just like I said above, you can't have like 2.2 atoms of something. It's either 2 atoms or it's not. You can't have decimal points when you're figuring out the proportions of the atoms in an element, or in a compound or a molecule. And then the example here is just the elements carbon and oxygen. They can form 2 compounds, CO2, carbon dioxide, and CO, carbon monoxide, and the ratio of the masses of oxygen is always a whole number. Again, no CO 1.5. That's just not going to happen. That's not possible. So these laws serve as the basis for understanding chemical formulas and reaction. 2 types of formulas that you might see and need to understand how to derive in the vocabulary associated with them are the molecular formula and the empirical formula. This is what you'll almost always see. You still need to understand what an empirical formula is, though, because it will show up in your chemistry life in college and later. So we've got the molecular formula, and it is a chemical formula that indicates the actual numbers and types of atoms in a molecule. Your example here is H2O2, and in fact, I don't know why that's not a subscript. H2O2, that should have been a subscript here, is the molecular formula for hydrogen peroxide. The empirical formula is a chemical formula that indicates the relative numbers. The relative numbers in the smallest whole number ratio. So for hydrogen peroxide, which we just now saw, the lowest whole number ratio for those is going to be HO. Okay, so because 2 will divide into itself both times and give you 1. And by the way, just a piece of knowledge for you, when you don't have a number, it is assumed to be a 1. So there's nothing here and nothing here, but it is assumed that there's 1 there. The same in the front, okay? If there's no number in the front, it's assumed that there's a 1. So you might have something that, looks like this, okay? That's okay. We need to have those 2s. But in chemistry, they don't ever put the 1s. Those are just assumed. So if there's nothing, just always know that that nothing is a 1. That might be very helpful when you're doing math problems to remember that. So let's move on into the structure of the atom. Most of this should be reviewed for you guys, but let's make sure that we understand, because year after year I still have people that don't know what subatomic particles are, don't know their charges or sizes, so we need to make sure that everybody understands that. So in the late 1800s, experiments showed that atoms are actually composed of several basic types of smaller particles, and that the number and arrangement of these particles within an atom, that's how I abbreviate within, by the way, within an atom, determine that atom's chemical properties. Super important, that atom's chemical properties. If you can understand the subatomic structure, you can understand how it's going to act, what its properties are going to be, what it's going to do or not do with other chemicals and other elements in atoms. Very important. Okay, so the atom is the smallest particle of an element that retains the chemical properties of the element. We've already said that. It consists of 2 regions. We have the nucleus, which is a positive charge. Always keep in mind, as we're talking about the subatomic structure, the charges of everything, because that's going to, again, we said that the number and arrangement of these particles, we could really say, and any charges. And charges, that word is not writing. Okay. Just catch my drift there, okay? You need to know. So the nucleus has a positive charge, and the electron cloud. Okay, it is not an orbital. It's not like the drawings on the Big Bang Theory that have, the nucleus in the middle and the electrons in these nice little circles, these nice little orbits. Okay, that's not really how electrons act, though we'll still see this kind of drawing because it is helpful for us to understand energy levels and potential areas that an electron might be located. But it is actually a cloud. The current model is the wave model, and we'll actually talk about that separately from these notes. So anyways, the electron cloud has a negative charge. The 3 subatomic particles are protons, neutrons, and electrons. You should know this. If you don't, commit it to memory right now. Protons, neutrons, and electrons. Okay, and note, protons and neutrons can further be divided into quarks. Quarks are a relatively new study, and we are not going to really get into them at this level. But they are there, and I want you to realize there is even further breakdown than what we're even going to get into in this class. So, the nucleus contains positively charged protons and neutral neutrons. The electrons are negatively charged. I have a table with all of this in it coming up, and you're going to need to know that table. Atoms are neutral or not charged. So, an atom must have the same number of electrons as protons. Must have the same number of electrons, that's how you can abbreviate that, as protons. And you can abbreviate protons with a P and a positive sign. Though neutrons can differ, and we're going to learn the terms for all of these things here in a minute. Okay, but if you are just talking about an atom, that word is differ. I need a better pen. Let me try that again. Differ. It's a little better. Okay, consider this truth. And again, this is why the charges matter. Like charges repel each other, unlike charges attract. So if this is the case, how does the nucleus of an atom not fly apart? You know, you would think if like repulses like, and the protons are all positive up there in the nucleus, that it would just fly apart. It's going to not stay together because they are repulsed by one another. So there's a force, a very important one, known as the strong nuclear force. It exists that helps hold the nucleus together. The strong nuclear force. I just wanted you to write that. Hopefully it would help you remember it. The strong nuclear force is a force that acts between subatomic particles that are extremely close together, the protons, to overcome the electrical repulsion of the protons in order to hold the nucleus together. So the structure and function of all matter is determined by electrical forces within, that's what we've just talked about, and between atoms. Now we'll talk about these forces between atoms when we get to bonding. So we're not quite done with this big idea in this unit. But we can compare the strength of electrical forces between particles by studying melting points, boiling points, vapor pressure. We're going to do this definitely. Boiling points and vapor pressure we're probably not going to do unless I find something that I think is going to be doable in our classroom for those. But these electrical forces are of fundamental importance in understanding the chemical behavior of atoms, and that's what we definitely want to understand, is that chemical behavior. All right, 2 more concepts here, and I think we are done. So you will need to know this table. It is going to be on your quiz. Parts of it are going to be in your test and in your final exam. And so what you have here, and I meant to leave blanks, but I don't guess I did. You have your electrons, protons, and neutrons, all of your subatomic particles. Okay, here are your symbols right here. E negative, P positive, N, and that is a 0. So let me write that bigger. Okay, a neutron is an N with a superscript 0. Because it has no charge. Let me try that again. I'm still not able to write that. N0. There we go. These over here, I am not going to use in this class. I think we're going to be doing well to just go on and get these basic ones done. The relative electrical charges are -1, +1, and 0. Again, we know the electrons are negative, protons are positive, neutrons are 0. And then they just threw the 1 on there for the to make it relative to one another. Your mass numbers are 0, 1, and 1. This is so important. You'll notice the protons and the neutrons have approximately the same mass, and in fact, let's go on and look at it. Your relative mass, we're only off starting right here. Okay, so we are very, very close in mass for the protons, positive protons, and the neutral neutrons. And then look how much smaller the electron is. Okay, so it, in relation to those, is just like having no mass at all. That's going to be very important. And here are their actual masses right here. Again, look how much smaller. We're to the 10 to the -34, where we're 10 to the -27 here. Much, much smaller. So again, this table above shows a proton and neutron. A proton, and you can abbreviate, and neutron are approximately the same size and are 2,000 times larger than an electron. So, if a large football stadium were an atom, this would make the nucleus, including the protons and neutrons, about the size of a marble. Did I say the atom? I think I meant to say the nucleus. Let me say that again. It is the nucleus I'm talking about. So the nucleus, let's say that this box is our football field, and you will have to draw this model or one that you come up with the relative sizes of the subatomic particles that you think is better. I think this is a great one though. So this is our atom, and you will need to label this atom. And say on the 50-yard line we have a marble, which represents our nucleus. Okay, remember the nucleus has protons and neutrons. You need to have all of these pieces for your open response on this exam. So you've got your nucleus here. That's about the size of the nucleus, about the size of a marble. And then the electrons, remember we talked above that the protons and neutrons are 2,000 times larger than the electrons. So the electrons would be similar to dust particles floating about the stadium. Or, I also like to say, or gnats. Little gnats flying around, because electrons are moving so fast that I think gnats are even a better analogy. So look how small. You'll notice there are red dots appearing here, but they are so much smaller. And then you'll just need to pick one of those and label it electrons. Okay? And so this is actually a relative scale model of the subatomic particles that you will need to know. So by looking at that, we know that atoms are mostly empty space. Look at all that empty space. All right. See you next time.